So we turn now to a very interesting question, and that is, how do we store electrical energy? And the first point we want to make is that if you look at renewable energy sources, and that includes wind power, solar photovoltaics, geothermal, hydroelectric, and concentrated solar thermal, every single one of those renewable sources produces electricity. And so we turn then to the question of how we store that and what the techniques are for storing this electricity that's created by wind, by solar input, and in particular those two vary. And as we'll see, wind power increases, of course, with wind speed, and wind speed increases when a low pressure area moves over a region. On the other hand, solar is the reverse. We have far more sunlight on a clear day under high pressure conditions. And as these storm systems move across a country, they're typically 1,000 or so miles across. So we have an interlacing between wind power at low meteorological pressure and solar power that increases with high meteorological pressure. So we want to examine how we deal with the variability of this input. So let's look at this pattern of varying electrical power demand on the electrical grid. We plot the variation in electrical power demand as a function of time. And we can pick any year. This happens to be January and June of the same year. And we can see, first of all, in January, the power demand in the winter is somewhat higher than it is in the summer. Now, you can immediately look at one of these plots and make a judgment about what latitude this is, because if more energy is going into heating in the winter than in cooling in the summer, it means it's a more northern latitude. As you move to southern latitudes, the cooling demand from air conditioning dramatically exceeds the heating demand. But we'll take this is a typical mid-latitude northern hemisphere case. But the first thing you notice is the remarkable variation. And if we look with high time resolution, we see that the peak occurs during the daylight hours, and that's primarily because people wake up in the morning and they start to use energy, and the energy demand on the grid increases very, very quickly. And this is an engineering problem that's been dealt with ever since electricity was a major part of the energy component of a national energy budget. And then as people go to bed, the demand drops down. Well, that means that in order to sustain this demand, you've got to match the voltage on that power distribution, maintain that voltage by raising the ability to generate electrical power in proportion to its demand. There's a very delicate balance between demand and supply on an electric grid. And so operators of electrical generating plants are profoundly active in the early part of every day because they have to ratchet up the amount of electrical power they're putting on the grid to balance the demand requirement. And similarly, at the end of the day, they have to back off on that rate of electrical energy production. So now let's look at the capacity factor for wind generation on the high plains of the central United States. And the capacity factor simply means the day in, day out production of electricity relative to the total generating capacity of a particular wind turbine. And a typical wind turbine puts out about 2.5 megawatts of power. That means a capacity factor of 0.5 would produce day in, day out 1.25 megawatts of power. Now, a capacity factor of 0.5 is remarkably high, but if we analyze the central part of the United States, for example, and I can do this for China or any other region, the capacity factor throughout the entire central part of the U.S. runs between 0.4 and 0.5, and that's remarkable. In fact, there are stories from the 19th century about the wind speed in the high plains driving people mad because it blew day in, day out. And it turns out when this is analyzed very carefully and quantitatively, it's a fact that the wind speeds, average wind speeds in the central part of the United States are extremely high. So now let's plot for a given position, and we'll pick number 5 right in the middle of this distribution. Let's plot the capacity factor as a function of day, so 10, 20, up to 90 days. And that's the red curve. Notice the remarkable fluctuation day in, day out. As the weather systems move through the central part of the continent, the wind velocities go from virtually nothing to extremely high, delivering a very high capacity factor briefly, but on average about 0.5. If we average over all of those 10 stations, we create the black line, and notice that it's far smoother. You can also notice the fact that we've selected stations in a fairly narrow longitude bin. That is, the east-west dimension is fairly small. It's also true that if we mix this with solar energy, the solar energy is out of phase with the wind energy, so when the wind energy is high, solar is low. When solar is high, wind is low, and this is a reason why it's so important to create a national grid.